In this lecture, let us discuss observability. What is observability? Let us consider an unforced system, unforced state equation or unforced system. Let us say it is x of k plus 1t is equal to g into x of kt and y of kt is equal to c into x of kt. Let us consider this equation, and that is unforced system in this case when our input u of kt is 0. U of kt is 0. That is, you are not applying any input to this system. Why? What is the need for us considering an unforced system is, for example, if we consider a system h into u of kt and d into u of kt. If we consider this system, let us say we know the equation or the solution of the state equation x of kt is equal to g power n x of 0, or I will consider this as x of nt. X of nt is equal to g power n x of 0 plus sigma j is 0 to n minus 1 g power n minus j h u of jt. Right. Now this is the solution of this state equation, and this state equation, when substituted in that, we will be getting our input or x of k plus 1t as this one, or y of kt is equal to c into x of kt, c into x of kt or nt. So I consider here, let us consider y of nt is nth dimensional nth sampling period, c into g power n x of 0 plus c into sigma j 0 to n minus 1 g power n minus j minus 1 h u of jt plus d u of kt. Now with this equation in mind, let us see that we know what is the value of c, we know what is the value of g, right? We know what is the value of h, and we know what is u of kt and d, right? We know all these are known quantities. All these are known matrices or known quantities, right? Known matrices, known quantities. Now we can say that if I know this value x of 0, it is sufficient for me to find out y of nt, right? So knowing this value, you can find this value y of t, because rest all are known. That is, these two are known quantities for us. These two sets, or you can say these two are known quantities for us. This factor in this equation and this factor also is known to us. When we know these values, then there is no point in again utilizing this and wasting the time in calculating what are the values of these things and all. So in order to reduce the manipulation errors or manipulations or calculations, you can directly go for an unforced system, where if you don't have this, let us see what is our now when u of jt is 0, what is the output? What is the solution of the state equation? You are having this equation x of nt, and therefore y of nt, what do we have? We have c into g power n x of 0. Now this is known, this is known. If we know this, we will know the output behavior, right? So without any problem, you can just with minimum of calculations, you can go and find out the output of the equation of the system. That is why we are going for an unforced system, right? So with this unforced system, let us consider to determine what is observability in this for this system. An unforced state equation, x of k plus 1t is equal to g into x of kt and y of kt is equal to c into x of kt. You can see that why they are, if observability defines that if it is possible in any linear time invariant discrete time control systems, this is in general for both controllability and observability, any linear time invariant discrete time control systems, if it is possible to find out x of 0, initial state, that is, if it is possible to determine the initial state by observing y of kt. By observing y of kt, is it possible for us to find out the initial state, determine the initial state of the system? X represents state of the system. in a finite time period, again n sampling periods. In a finite time period, that is n sampling periods, that is a constraint for us. If it is possible for us to determine the initial state x of 0 by observing y of kt within a finite time period, n sampling periods, then it is said to be observable in nature. Right, then this system is observable in nature. Not only this system, any system is observable in nature of this sort. Linear time period, discrete time control systems. Right, to minimize the calculation, we are going for an unforced system. Now this observability is playing a major role in finding out the state feedback of the system. Right, state feedback of this system, feedback analysis of the system requires the state variables to be measured, and a few state variables may be unmeasurable, a few state variables may be measurable. Measurable in the sense it is necessary for us to find out the initial state by observing the output. That is called observability. So observability plays a very major role in pole placement techniques, in Ackermann's formula that we are going to use. Therefore, in state feedback system, that is how we are going to find out x of 0 or determine x of 0 from observing y of kt. Right. So this is observability and the definition of observability, and let us see what is the observability matrix of this form. Now we know that what is the solution for this state equation? You have x of kt. Let us say this is the solution for this state equation. It is nothing but, or x of nt, you can say g power n x of 0. Right. Now what is our equation? Y of kt or y of nt is equal to c into g power n x of c into g power n x of 0. Now let us find out what are the various. X of 0 is a state vector, y of nt is the vector which we are going to find out the output of the system, and this exists from y of 0t, y of 1t, y of 2t, so on, y of nt. Now this is our equation, right? And when for this equation, what is it that we are getting? C into g power 0, c into z power 0, x of 0, c into, now if I consider this as an equation, y of 0, y of nt, because this is a y of nt, or you can consider it as y of mt or y of rt, any output, because it is a multi-output system. You can go for m number of things, and c, then cg, then cg square, so on, cg power n into x of 0. Okay, now C is a matrix. C, you know it is a matrix of that form, right? And x of 0 is x10, x20, so on, xn0. And C is a matrix, is a row matrix. CG is also a row matrix, right? Because this is, if let us say if this is an n by 1 or m by 1 vector, and this is an n by 1 vector, and C is m by n vector. It has both rows and columns. Therefore, you can find out all the values. So you can say we are having these values here. So you are separating this. This is a matrix. This is a matrix. All these are matrices, right? And those matrices are m by n matrices. C into Cg. C into G gives us C into G. C is m by n and G is n by n. Therefore, you have m by n matrix everywhere. M by n matrix if it is going for. And if you want how many number of output variables are required in your system, you can consider so and so. Therefore, you can find out what is the number of outputs that are available in this system, right? So eventually, you will be having this equation, right? And when this equation is considered, you will be having, this is called the observability matrix here. observability matrix. This is called the observability matrix. Now, the observability matrix, we'll have to work on this observability matrix and tell whether the system is completely observable or not. Now, what is the meaning of observability? That is, you need to find out or determine the initial state of the system by observing the output variables, output of the system at different instance of time, but within a finite time period. If it is possible for us to observe the output variables for a particular time period and determine the initial state, then you can say that it is completely observable. And for this, what is the rule? You will have to find out the rank of this matrix again. Rank of this matrix, if it is equal to n, the number of rows of this column, if it is equal to n, then you can say that the system is completely observable. Right. And with this in mind, we can say that, for example, a pole zero cancellation is occurring in a transfer function. For example, y of z by u of z. Y of z by u of z is equal to, let me say, where we have z plus 1, z plus 4 by z plus 1, z plus 2 and z plus 3. Let us say, now you can consider that z plus 1 and z plus 2. This is a 0 and this is a pole. A pole zero cancellation occurs whenever in your transfer function, if there is any pole zero cancellation that is occurring, you can say that this system is not controllable as well as not observable. Right. If there is any pole zero cancellation occurring in this system, z plus 1 and z plus 1, then automatically you can say that the system is neither controllable nor observable. It may be either state controllability or output controllability and observability. And all these three are not possible for such pole zero cancellations. Right. So when you are going for observability and controllability tests, you need to first find out in discrete time control systems, if you are having your pulse transfer function of this sort, y of z by u of z, then the system is not controllable and also not observable in nature.